In this video, we will look at electrostatic precipitators. As with gravity settlers and centrifugal separators, ESPs are used for the removal of primary particulates from a gas stream.
Now, electrostatic precipitators are very commonly used. They're, in many respects, we'll talk about baghouse filters next. In many cases, they've replaced baghouse filters. These are used in the power electric production industry for removing fly ash. They're removed in the cement kiln industry or the cement industry to remove kiln dust. They're removed in a number of chemical processing facilities, for instance, to remove tar, in metal processing, in lead smelters, paper and pulp to remove alkali salt. So significant number of processes that are using these electrostatic precipitators. The difference between an electrostatic precipitator and many of the other units that we've talked about or will talk about is that the forces of collection act only on the particles. So the gas is not affected by the process itself. And it can be used for both dry dust or liquid droplets, so it's extremely versatile. And it's able to remove particles that are much smaller than what we could remove with either a gravity settler or centrifugal separators. So look at a few of the advantages and disadvantages. Very high efficiencies. You can get 99.9% removal of particulate matter, and that includes very small particulates. So you can actually, compared to gravity settlers or centrifugal separators, you can remove particles that are less than 5 microns in size. We can also handle large flow rates, and it has a low pressure drop. So one of the problems with the centrifugal separators is the pressure drop. When we talk about baghouse filters, the pressure drops are even greater with a baghouse filter than it is with these other processes. We can also operate it with either, as I mentioned, either wet or dry collection. You can also, with dry collection, actually use it for reclaiming material. So for valuable material, reclaiming it is important. It can be operated over a wide temperature range. Unless you're operating at very high efficiency, it has low operating costs. It can handle heavy dust loads. It's durable. There's very little maintenance, and it has a long service life. On the other hand, the biggest disadvantage is right here is the capital cost. It has high capital costs. Now, in some cases, you have a gas stream that you need to remove gaseous contaminants. And so, for instance, SO2. This is not going to remove SO2. It will remove the particulates, but it will not remove any gases like SO2, NO, NO2, etc. It is also not very flexible with changing operating conditions. And this was a major problem back in the 1990s with the Clean Air Act amendments. What happened was, because of the amendments, there was a move from using high sulfur coal to using low sulfur coal. And the idea was that that would decrease SO2 emissions. A number of power plants had put in electrostatic precipitators. Those electrostatic precipitators were working quite well until they made the switch in the coal. They made the switch in the coal, and all of a sudden now the electrostatic precipitators were not working like they had previously. And these power plants are emitting much higher concentrations of SO2 than one would predict. Well, the problem was, it's kind of tied here, that the removal is very much dependent on the particle resistivity. And changing the coal had an effect on particle resistivity, which had a resulting decrease in the efficiency. And what they had to do was actually modify the gas stream in order to restore that efficiency, which ultimately they did, but it took a while to figure out what was going on here. So changing operating conditions can have a detrimental impact on removal efficiencies. They also require a lot of space. They don't work on all particles. They don't work on particles with very low or very high electric resistivity. They also operate better at steady state. So changing operating conditions can have a detrimental impact. The one I mentioned was a major change in the coal, so the source material, but also variable properties of the gases can have a detrimental impact. They don't work very well on sticky particles, particles like tar, gelatinous material, that's hygroscopic material that tends to stick to things. And they can also be a potential fire hazard. You've got, as you'll see, get a corona discharge to create a corona to produce an ionizing field. So what we're doing with these is we have a gas stream. So you can see here, the gas stream in. We have a series of electrodes. And what we do is we ionize the particles. So you're inducing a charge in the particle. The particle then is able to migrate to a collection plate. You dissipate or neutralize that charge, dislodge the particles, and then they fall into a hopper, and you've got clean air coming out the top. You can see that in this figure here. So you can see here, you've got a metal grid that's negatively charged. So you're inducing a negative charge in the particles. You've got a positively charged collection plate. So your particles move towards that collection plate. They ultimately fall into this collector here. And then what happens is you shake, wrap these plates. That causes the particles to fall into a hopper, and then they can be collected and either treated, disposed of, or reused. And then you've got clean air coming out the top. See here a larger unit. So it's a cutaway of these. You see these plates here. So you see these very large plates. The gas comes in. It's flowing across these plates. It's being charged. So those particles are being charged. They move towards the plate, the collector, and then are collected there. And eventually you can see they will fall into the hopper. So you've got a high voltage system. So in terms of energy, this is much more energy consumptive than your centrifugal separator. On the other hand, you have the problem of, or the advantage that you can remove much smaller particles here than you could with a centrifugal separator. Just going to walk you through some images. These were actually taken by about 8 years ago by a then MSU student, who's now an alumna. It's taken at the Eckert power plant and part of the BWL system. It actually has been recently decommissioned. Because I have these images in here, I will post this on YouTube. There will be a link on Kappa, but I won't have it won't be unlisted because of this. So to give you some images, this is Emily's little story as she was, you'll see some pictures of her. So basically for inspections and maintenance, there's hatches at the base and also at the top of the precipitator so that one can go in and inspect these and also do maintenance. So this is looking down from the top hatch, and you can see these rows of plates, and you see the charging rods down the side. And here, this was Emily entering from the top hatch. You can see that there's minimal headspace, and now she's looking between the plates, and what she's doing is checking for warping. And these plates can warp if there's too much heat stress, and if the plates are too close to one another, that will decrease the efficiency. If the efficiency is decreased, then they're in danger of violating the air permit. And if you remember about measuring opacity, so what they're doing is they're measuring opacity, and she's making sure that there isn't this warping so that they don't violate the opacity rules. This is another image from the top. It's about 13 stories down. The objects to the left, right here, here, here. These are the wrappers, and these hit the plate, and that causes the fly ash to fall, will collect below in the hopper, and they sell the fly ash as a concrete additive. This is just another view of the plates and the charging rods. So this is looking down from the top. And this is a view from the base walkway. So it's entering from the side of the precipitator, and on the left and right are the sets of plates. So I thought this was just interesting to give you a sense of what the inside of one of these units look like. So as the gas moves through the electrostatic precipitator, the concentration of the particles will decrease because of the net migration of these particles to the plate. This equation is referred as the Deutsch-Anderson equation, and it's derived from a mass balance on the particles that are flowing in and out of the electrostatic precipitator. Now, that collection efficiency is dependent on a terminal drift velocity. That's the terminal velocity of the particles as they approach the collection plate, those plates that you saw, when it's under the influence of the electric field. A is the total area of all of those plates that you saw in those images, and Q is the volumetric gas flow rate. Drift velocities typically are determined from either pilot studies or field experiences, and they range from, for instance, for coal fly ash, they range from about 2 to 20 centimeters per second. For cement dust, they range from about 6 to 7 centimeters per second. For blast furnace, they range from about 6 to 14 centimeters per second, just to give you a sense of the range of these. And you can use any set of units in this equation here as long as your units are consistent. So you're going to use feet per minute for the drift velocity. You're going to use feet squared for the area of the collection plate, and feet cubed per minute for the volumetric flow. If you use meters per second, then you're going to use meters squared. And you're going to use meters cubed per second for your flow rate. So this would be W, this would be area, and that's your flow rate. Okay. So just make sure that your units are consistent when you're using this equation. The development of this equation assumes that the particles are smooth and spherical. Also assumes that gases and particles move in the x direction at constant velocity with no longitudinal mixing. And the particles are uniformly distributed in the x and y directions. So x direction is as it's moving along those plates. And we're assuming that the charging in the collection electric fields are constant with time and they're uniform. We'll also assume that the gas flow rate is constant and that reentrainment is negligible. So let's look at one example. We have an electrostatic precipitator and it has 6,000 meters squared of collection plate area. This is not unusual. It is 97% efficiency in treating flue gas at a flow rate of 200 meters cubed per second. It happens to be from a 200 megawatt power plant. And the question that is asked is, how large would the plate area have to be to increase the efficiency to 98% or say 99%? So we have the situation where the area is 6,000 meters squared. Efficiency is 97%. Q is 200 meters cubed per second. Got our efficiency equation here. So based on this situation where we have 97% efficiency, that is equal to 1 minus e to the minus. Now we don't know the drift velocity, but we know the area is 6,000 meters squared and the flow rate is 200 meters cubed per second. So we can calculate the drift velocity, and that drift velocity is 0.117 meters per second, or approximately 12 centimeters per second. Given that, we now then can calculate the area. So we've got the drift velocity. Assuming that drift velocity isn't going to change, conditions change, we're just asking how much bigger of an electrostatic precipitator would we need. So now we have 0.98 equals minus 1 minus e to the minus 0.117 meters per second. Now we're looking for the area, and we'll divide by 200 meters cubed per second, since the area doesn't change. And we find that we need about 6,700 square meters. So we need about 700 square meters more in order to obtain that additional 1% removal efficiency. If we then look at 99%, again, we're looking for area, divide by 200 meters cubed per second, and the area we calculate would be 7,900. So we've gone from 97%, where we needed 6,000 meters squared. We want to increase it to 98%. We need another 700 square meters. If we want to increase it to 99%, we need another 1,200 meters squared of air. So you can see that these get significantly larger the greater the removal efficiency that you need. And lastly, just to look at where we would be looking in terms of removal, just comparing it. We talked initially about a drop box. So I'm just going to switch to the highlighter. So we talked about a drop box. We're looking in this range. So we're looking at particles typically somewhere between about 20 microns or greater. If we're looking at cyclone separator, we're looking at somewhere between about 1 to 100 microns. We'll talk about scrubbers and fabric filters later. But if we're looking at electrostatic precipitators, we're down in the submicron size range. So you can see much greater removal of these smaller particles. You're not going to use a drop box to remove a micron size or submicron size particle. In fact, at that point, you're really looking at electrostatic precipitators. And we needed these in order to achieve the ambient air quality that we now have from prevent the deterioration from chemical plants, power plants, and other sources of these particulates. So I will end there. If anyone has any questions, I'm happy to answer them.